Right now, in the year 2026, the standard model of the universe is failing. Not in a subtle way, not at the edges. 3 independent datasets, collected by 3 independent instruments, are returning results that the model cannot explain. The first, the expansion rate of the universe gives 2 incompatible numbers, depending on how you measure it. The second, the James Webb Space Telescope is seeing galaxies that should not exist. And the force that drives the expansion of the cosmos may not be constant. None of this was supposed to happen. For 25 years, this model held. It described the age of the universe, the structure of galaxies, the temperature of the oldest light. It earned a Nobel Prize. It became the foundation. And now the foundation is cracking. Behind every crack, there is a theory, not a speculation. A published, peer-reviewed, mathematically precise theory that the scientific community has verified and then quietly stepped away from. Not because the theory is wrong, because the conclusion is uncomfortable. To understand why, you have to understand the model, what it is, what it promised, and why an entire generation of physicists trusted it. The model is called Lambda-CDM. Lambda stands for the cosmological constant, the name we gave to the force that is accelerating the expansion of space. CDM stands for cold dark matter, the invisible substance that holds galaxies together. Together, these 2 components account for 95% of everything in the universe. The remaining 5% is ordinary matter, you, stars, planets. That is everything you have ever seen or touched. 5%. The model was built to explain the other 95. It was born in 1998, when 2 teams independently discovered that the universe is not just expanding, but accelerating. Saul Perlmutter led one team. Adam Rees and Brian Schmidt led the other. They were measuring the brightness of distant Type 1a supernovae, explosions so uniform that they serve as cosmic measuring sticks. The supernovae were dimmer than expected. The only explanation that fit was that something is pushing space apart and the pushing is getting stronger. No one knew what this force was. We still do not know. We called it dark energy and gave it a Greek letter and moved on. Moving on meant testing. By 2003, data from the Wilkinson Microwave Anisotropy Probe confirmed that the model worked. It predicted the temperature fluctuations in the cosmic microwave background to extraordinary precision. It predicted the distribution of galaxies across billions of light years. It predicted the ratio of hydrogen to helium forged in the first 3 minutes after the Big Bang. Every test it faced, it passed. The reward came in 2011. Perlmutter, Rees, and Schmidt received the Nobel Prize. The prize cemented the model. Textbooks were rewritten. With the textbooks came something more powerful. The model became consensus. And consensus in physics is a dangerous word. It does not mean the universe agrees with you. It means your instruments are not yet precise enough to show you where you are wrong. The instruments got precise enough in the 2020s, and the first thing they showed us was a number that does not add up. That number is the expansion rate of the universe, called the Hubble constant. It tells you how fast galaxies are moving away from each other. There are 2 ways to measure it. The first is direct. Direct means this. You point a telescope at a Type 1a supernova, the same kind of explosion that led to the discovery of dark energy. You measure how bright it appears. You compare that to how bright it should be. You get the distance. From the distance and the redshift, you get the speed. The SHOES team, led by Adam Rees, has done this with hundreds of supernovae calibrated against Cepheid variable stars. Their answer is 73 kilometers per second per megaparsec. The second method does not look at the universe today. It looks at the universe as it was 380,000 years after the Big Bang. To look that far back, you take the cosmic microwave background, the oldest light in existence, and you feed its pattern into the Lambda-CDM model. You let the equations run forward 13.8 billion years. The Planck satellite did this with the most detailed map of the CMB ever made. Their answer is 67. 6 is not a large gap, but both measurements are extraordinarily precise. How precise? The SHOES team reports an uncertainty of roughly 1%. Planck is even tighter, less than 1%. When you account for the precision, the probability that this discrepancy is a coincidence drops below 1 in a billion. In particle physics, that level of confidence has a name. The name is 5 sigma, and 5 sigma is a discovery. This discrepancy exceeds 6 sigma. The obvious question was whether one side had made a mistake. The answer came in 2025, when the James Webb Space Telescope re-examined the SHOES calibration. It resolved individual Cepheid stars that Hubble could only see as blurs. The measurement did not change. JWST ruled out calibration error at 8 sigma. 2 numbers, both verified, both correct, both incompatible. What sits between them is not a mistake. It is a gap in the physics. That gap points in a specific direction. The direction is this. If the physics connecting the early universe to the present one is incomplete, then our picture of the early universe may also be wrong. And in 2022, we got the first direct evidence that it is. The evidence came from an instrument that was not built to break cosmology. It was built to see further than any instrument before it, to capture infrared light from the first galaxies that formed after the Big Bang. It did exactly that, and what it saw was not supposed to be there. What was not supposed to be there? At a redshift of 10 and above, meaning less than 500 million years after the Big Bang, JWST found galaxies. Not faint smudges, not proto-galactic fragments, fully formed, massive, structurally complex galaxies with billions of stars. Labbe and colleagues published the first results in 2023. The stellar masses they calculated exceeded the maximum that the Lambda-CDM model allows at that epoch. Not by a small margin. The masses were above the theoretical ceiling. Think about what that means. What it means is that the model does not merely underpredict the number of early galaxies. It predicts a maximum possible mass, a hard limit set by the available matter and the available time. The observed galaxies exceed that limit. The model says these objects cannot exist. The telescope says they do. You might argue that the problem is in galaxy formation, not in cosmology. Perhaps stars formed more efficiently than we assumed. Perhaps feedback mechanisms were weaker. Perhaps the initial conditions were different. These are reasonable objections. But every attempt to explain the excess within Lambda-CDM requires pushing the parameters to their extreme values simultaneously. Pushing everything to the extreme reveals a pattern. The model does not break in one place. It strains everywhere at once. The strain has a single meaning. The early universe, as seen by the most powerful telescope ever built, does not match the universe that the standard model predicts. And the disagreement is growing with every new observation. The numbers do not add up. The objects should not exist. And in April 2024, the third blow landed. The Dark Energy Spectroscopic Instrument, DESI, released its first-year results from the largest three-dimensional map of the universe ever constructed. DESI measures baryon acoustic oscillations, the faint imprint of sound waves that traveled through the early universe in its first 380,000 years. These sound waves left a characteristic pattern in the distribution of galaxies, a cosmic ruler that allows you to track how the expansion of space has changed over time. For 25 years, every measurement of this expansion was consistent with a cosmological constant, a fixed value of dark energy that does not change. DESI's data hinted at something different. The measurements, when combined across multiple redshift bins, suggested that dark energy may not be constant. It may be evolving. The significance is not yet at the level physicists demand for a definitive claim, but the direction is consistent across the dataset. And the implication is severe. Lambda is not just one parameter among many in the model, it is the foundation. The entire framework of Lambda-CDM is built on the assumption that the cosmological constant is constant. If it is not, the model does not need a correction. It needs a replacement. The community knows this. They showed it openly. In April 2024, the Royal Society titled a meeting challenging the standard cosmological model. 2 years later, the doubt was quantified. In May 2026, the largest survey of physicists ever conducted was published. Lambda-CDM did not receive majority support. The reason is simple: 3 instruments, 3 independent datasets, 3 results that the standard model cannot accommodate. The model that described the universe for a quarter of a century is failing. And the reason physicists are unsettled is not the failure itself. It is what comes next. Because if the model is wrong about the present, it is also wrong about the future. For 25 years, the future of the universe was settled. Not hopeful, but settled. If a dark energy is a cosmological constant, the math leads to one outcome and there is no way around it. That outcome is dictated by a single law. The second law of thermodynamics is the only law in physics that tells time which direction to go. Entropy increases. Order decays into disorder. Energy spreads out and cannot be gathered back. This has been known since 1865, when Rudolf Clausius first stated it. Clausius described what happens. A decade later, Ludwig Boltzmann showed why. Order is one arrangement among an astronomical number of disordered arrangements. The universe moves toward disorder not because something pushes it, but because there are overwhelmingly more ways to be disordered than to be ordered. You do not need a force, you need probability. And probability does not make exceptions. If probability makes no exceptions, then the timeline is calculable. Fred Adams and Gregory Laughlin calculated it in 1997. They divided the future into 5 epochs. The Stelliferous era ends in roughly 10 to the power of 14 years, when the last red dwarf stars burn out. The Degenerate era follows, dominated by white dwarfs, neutron stars, and cooling remnants. By 10 to the 40th, protons themselves decay. Matter as we understand it ceases to exist. The black hole era stretches to 10 to the 100th, when the last supermassive black holes evaporate through Hawking radiation. After that is the dark era. No structure, no gradient, no process. A uniform bath of photons with nearly zero energy, stretching across a space so vast that no 2 particles will ever interact again. But here is the part that is rarely discussed. In 1961, Rolf at Landauer proved that information is physical. Erasing a single bit of data releases a minimum amount of energy. KT times the natural logarithm of 2. The cost of processing one thought is real and measurable. At maximum entropy, when all gradients are gone and no energy differential remains, the cost of a single computation becomes infinite. The heat death of the universe is not merely the end of stars, it is the end of thought. A universe in which it is physically impossible to process a single bit of information, not dark, not cold, unthinkable. In the most literal sense of the word, the heat death is absolute. No law of physics offers an escape, but it is slow. The timeline stretches across numbers so large they lose all human meaning. And for decades, that distance provided a kind of psychological shelter. The end is real, but it is not our problem. That shelter depends on one assumption. It assumes dark energy is constant, a fixed value, a permanent feature of the vacuum. If DESI is right, and dark energy changes over time, the shelter disappears. What the disappearance looks like depends on a single variable, identified by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg in 2003. The equation of state of dark energy is described by a parameter called W. If W equals -1, dark energy is a cosmological constant. Expansion accelerates, but at a steady rate. The universe dies slowly. If W is greater than -1, dark energy weakens over time, Expansion slows. Gravity might eventually win. That path leads to a different ending, which we will return to. But if W is less than -1, something else happens. Dark energy does not just push space apart, it pushes harder over time. The force itself grows. Caldwell called this phantom energy. And phantom energy has a consequence that no other cosmological scenario produces. It tears things apart, not metaphorically, physically, in sequence. The expansion first overwhelms gravity at the largest scales. Clusters of galaxies lose their gravitational binding and fly apart. Then individual galaxies, then star systems, then planets separate from their stars. Then the electromagnetic force holding molecules together is overpowered. Then nuclear forces. Atoms come apart. Then spacetime itself. Each step has a number. Caldwell calculated them all. Billions of years before the end, galaxy clusters dissolve. Millions of years before, the Milky Way disintegrates. Months before, the solar system flies apart. Minutes before, the Earth is ripped apart. Fractions of a second before, atoms cease to exist. This is the Big Rip. And the variations do not help. Frampton and colleagues showed in 2011 and 2012 that even if you never quite crosses -1, softer versions of the same process still destroy every gravitationally bound structure in the universe. The choice is not between catastrophe and safety. It is between which kind of catastrophe. The Big Rip assumes dark energy is getting stronger. But DESI's data allow another possibility. What if dark energy is getting weaker? If the force that is pushing the universe apart is fading, then at some point gravity takes over. Expansion slows, stops, reverses, and the universe begins to collapse. This is the Big Crunch. The name is old. For most of the 20th century, the Big Crunch was the leading candidate for the fate of the universe. Before 1998, most cosmologists assumed that the expansion was decelerating, that gravity would eventually win, and that the universe would end not in silence, but in compression. Everything falling back toward everything else. Galaxies merging, stars colliding, space shrinking, temperature rising, the cosmic microwave background blue shifting from microwave to infrared, to visible, to ultraviolet, to gamma. In the final moments, the observable universe would compress into a volume smaller than an atom, and the laws of physics as we know them would cease to apply. None of it happened. The discovery of accelerating expansion in 1998 killed this scenario. If dark energy is a constant, gravity never wins. The Big Crunch was declared dead and removed from serious consideration. It stayed dead for 27 years. 27 years later, it moved. Models published by Henry Tai at Cornell in 2025 showed that if dark energy decreases with time in a manner consistent with DESI's data, the Big Crunch becomes possible again. Not confirmed, not predicted, possible. For the first time since the discovery of dark energy, the data do not rule it out. 3 scenarios. The heat death, slow and absolute. The Big Rip, violent and sequential. The Big Crunch, a reversal that ends in compression. All 3 depend on one variable, the behavior of dark energy over time. And we do not know what dark energy is. We named it. We measured its effect. We have no theory that explains it. The force that determines how the universe ends is the force we understand least. But all 3 scenarios share one feature. They describe the end of things. Matter, stars, structures. What they do not touch are the rules. The laws of physics remain intact while the universe dies within them. There is a 4th scenario in which even that assumption fails. Every scenario we have considered so far operates inside the same framework. The heat death assumes the laws of thermodynamics hold forever. The Big Rip assumes the equations of general relativity remain valid as space tears apart. The Big Crunch assumes gravity works the same way on the largest scales as it does on the smallest. In each case, the universe dies, But the rules survive. The content disappears. The structure that governs it does not. We find this comforting. If the rules are permanent, we can at least understand the ending even if we cannot prevent it. But in 2012, the largest experiment in the history of physics produced a measurement that puts this comfort in question. The Large Hadron Collider at CERN detected the Higgs boson. The discovery confirmed a prediction that had been waiting for nearly half a century. It completed the Standard Model of particle physics. Completing the Standard Model earned Peter Higgs and François Englert the Nobel Prize. But the number attached to the discovery carried an implication that received far less attention. The mass of the Higgs boson is 125.1 giga-electron-volts. And that number, when fed into the equations that describe the behavior of the quantum vacuum, places our universe in a region of parameter space that physicists had hoped to avoid. The rules that govern the universe may not be permanent after all. They may be contingent on a state that can change. And if that state changes, the rules change with it. Not slowly, not gradually, at the speed of light. To understand what the Higgs mass implies, you have to understand what the vacuum is. The word vacuum suggests emptiness, a void, the absence of everything. But in quantum field theory, the vacuum is not empty. It is a state. Specifically, it is the lowest energy state of the quantum fields that permeate all of space. Every point in the universe is filled with these fields. The electromagnetic field, the Higgs field, the quark fields. When none of them are excited, when no particles are present, you have the vacuum. But the vacuum still has energy. And the configuration of that energy determines the laws of physics. The masses of particles, the strengths of forces, the way atoms hold together. All of it depends on which vacuum state the fields are sitting in. The question is whether there is more than one state to sit in. In 1977, Sidney Coleman answered it. He showed that a quantum field can have more than one minimum. Think of a ball resting in a valley between two hills. It is stable. But if there is a deeper valley on the other side of one of the hills, the ball is not in the true minimum. It is in a local minimum, a false vacuum. The ball can stay there for a very long time, but quantum mechanics allows something that classical physics does not. The ball can tunnel through the hill without climbing over it. No trigger is required. No external force, no warning. The transition is spontaneous. It is governed by probability, not cause. That calculation ignored gravity. 3 years later, Coleman and Frank DeLucia included it. The result was worse. In a universe with gravity, the tunneling does not just change the energy of the field, it changes the structure of spacetime itself. The false vacuum does not quietly settle into the true one. It detonates. Coleman's calculation was theoretical. It described a possibility, not a measurement. The question was whether our vacuum is the true minimum or the false one. For decades, there was no way to answer that question. The answer required knowing the precise values of two numbers: the mass of the Higgs boson and the mass of the top quark. The top quark mass had been measured at Fermilab in 1995. The Higgs mass remained unknown until July 4th, 2012, when CERN announced the detection of the Higgs boson at 125.1 giga-electron-volts. Within months, theorists mapped the result onto the stability diagram of the electroweak vacuum. The mapping was done twice, first by Degrassi and colleagues in 2012, then refined by Butazzo and colleagues in 2013. The diagram has three regions. In one region, the vacuum is absolutely stable. The universe sits in the deepest possible valley. There is no lower state. No transition is possible. In another region, the vacuum is unstable. The transition would have already happened. We would not be here. The third region lies between the two, metastability. The vacuum is not in the deepest valley. A deeper one exists, but the barrier between them is high enough that the transition has not yet occurred. It could occur. It will occur, given enough time, but it has not occurred yet. The measured mass of the Higgs boson places our universe in the third region, not stable, not unstable, metastable, balanced on a ledge that quantum mechanics guarantees we will eventually fall from. The largest experiment in human history did not tell us the universe is safe. It told us the universe is waiting. What happens when the waiting ends? The transition begins at a single point. A quantum fluctuation. A random event in a random location. No cause, no trigger. At that point, the Higgs field drops to its true minimum. The laws of physics in that region change instantly. The mass of the electron changes. The strength of the nuclear force changes. The way atoms bind together changes. Chemistry as we know it ceases to be possible. This new state of the vacuum is more stable than the one we inhabit. And it expands. Coleman calculated the geometry of the expansion in 1977. The boundary between the new vacuum and the old one forms a bubble. The wall of the bubble moves outward. It accelerates. It reaches the speed of light. Inside the bubble, the universe operates under different rules. Outside, everything is still normal. You're still reading. Stars are still burning. But the wall is coming. And here is the fact that separates this scenario from every other threat in this video. You cannot see it coming. Light is the fastest signal in the universe. Information cannot travel faster than light. The wall of the bubble moves at the speed of light. This means the wall arrives at the exact same moment as the first photon that could have warned you. There is no flash on the horizon. No dimming of the stars. No tremor in the instruments. The bubble does not announce itself. One moment the universe is here. The next moment, it is something else. The transition is not death in the way you understand death. It is a replacement. The laws that defined what matter is, how forces behave, and what structures can exist are gone. Every particle, every force, every constant is reassigned. What was matter becomes something that has no name in our physics, because our physics no longer applies. There is an obvious objection. If this transition is so dangerous, why has it not already happened? The universe is 13.8 billion years old. Quantum fluctuations have been occurring since the beginning. If the barrier were easy to tunnel through, the vacuum would have decayed long before life had time to evolve. That argument has a sharper version, posed by Piet Hut and Martin Rees in 1983. What about high-energy collisions? Cosmic rays, protons accelerated to enormous energies by astrophysical processes, slam into particles in the upper atmosphere every second. Some of these collisions reach energies far beyond anything the Large Hadron Collider can produce. If a high-energy collision could trigger vacuum decay, it would have been triggered billions of years ago. We exist. Therefore, that trigger does not work. The conclusion held. It was formalized in the LHC Safety Report of 2003 and confirmed by subsequent analyses. The known triggers are excluded. But there is a subtlety that the safety argument does not cover. It excludes triggers that have already occurred in the history of the universe. It does not exclude triggers that have never occurred. A quantum fluctuation of a type that has not happened in 13.8 billion years is not impossible. It is improbable. And in a universe that may last forever, improbable is not the same as never. The probability of vacuum decay in any given region of space in any given year may be unimaginably small, but it is not zero. And over an infinite timeline, a non-zero probability becomes a certainty. The vacuum is not safe, it is patient. It is held for 13.8 billion years, which tells us only that the barrier is high. It does not tell us the barrier is permanent. The metastability of the vacuum means that the laws of physics are not given. They are contingent. They depend on which valley the Higgs field occupies. In a different valley, the electron has a different mass. The proton may not hold together, carbon may not form. The fact that we exist in this particular configuration of the laws is not guaranteed by anything deeper. It just happens to be the valley we are in. Which raises a question that physics has struggled with for half a century. Why this valley? Why these constants? There are at least 26 fundamental constants in the standard model of particle physics. the speed of light, the gravitational constant, the masses of quarks and leptons, the strengths of the four fundamental forces, the cosmological constant. None of them are derived from a deeper theory. None of them are predicted. They are measured. And when you examine the values, something disturbing emerges. They are fine-tuned. The precision is extreme. Adjust the gravitational constant by 1 part in 10 to the 36th, and stars cannot form. Alter the strong nuclear force by 2%, and carbon cannot be synthesized inside stars. In 1953, Fred Hoyle predicted a resonant state in the carbon-12 nucleus purely because he reasoned that without it, carbon could not exist, and neither could we. The resonance was found exactly where he predicted. Hoyle himself said the result looked like the universe had been designed. He did not mean it as a compliment, he meant it as a problem. Because the precision is so extreme and so widespread across the constants, that it demands an explanation. And no explanation has been found. There are 3 possible explanations. Each one is unacceptable to a significant portion of the scientific community. The first is coincidence. The constants happen to have these values by chance. The probability of this coincidence, calculated across all 26 constants, is so small that writing it out would require more zeros than there are atoms in the observable universe. Physicists do not reject coincidence because it is uncomfortable. They reject it because science is built on the premise that extreme improbabilities demand explanations. If you roll a die and get a 6, that is chance. If you roll it 1,000 times and get a 6 every time, you do not say the die is fair. The second explanation is design. Some agent, some intelligence, some process selected these values. This explanation is logically coherent. It is also scientifically untestable. It makes no predictions. It cannot be falsified. It is not within the domain of physics, and any physicist who raises it in a professional context knows the cost. The third explanation is the one the community has reluctantly adopted as the least objectionable. It is the multiverse. If there are an enormous number of universes, each with different values of the constants, then we inevitably find ourselves in one where the constants allow observers to exist. The version that dominates physics departments is the string landscape, developed by Leonard Susskind and others in the early 2000s. String theory allows roughly 10 to the 500th possible vacuum configurations. Each one is a universe with its own physics. We are in this one because this is the one that produced us. This is the anthropic principle, formulated by Brandon Carter in 1974, and it has a problem. It is not an explanation. It is a tautology. It says we observe a universe compatible with observers because we are observers. It describes the fact. It does not explain the cause. Despite explaining nothing, the multiverse is the consensus answer among theoretical physicists who engage with the fine-tuning problem. But consensus here does not mean confidence. It means exhaustion. The alternatives are worse, so the community settles on the option that at least has a mathematical framework, even if that framework cannot be tested. The option comes with a number. Susskind's landscape offers 10 to the 500th possible vacuum states. Each one a universe, each one with its own constants. The math is internally consistent, but no observation we can ever make will confirm or deny the existence of these other universes. They are beyond our cosmological horizon. They are beyond any cosmological horizon. The multiverse is a theory that explains everything and predicts nothing. In the philosophy of science, that is not a theory. It is a metaphysical postulate, and the anthropic principle that accompanies it is no better. Carter's formulation is straightforward. We observe the universe to have properties compatible with our existence because if it did not, we would not be here to observe it. This is true. It is also empty. It is the equivalent of surviving a plane crash and concluding that the crash must have been survivable because you survived it. It tells you nothing about why the plane crashed, how you survived, or whether you will survive the next one. Fine-tuning remains the question that physics cannot answer within its own framework. Every response either invokes the untestable, the unscientific, or the circular. And this is why the topic is discussed quietly. Not because the data are uncertain. The data are among the most precisely measured in all of physics. But because every honest path from the data leads to a conclusion that does not fit inside the method. Fine-tuning asks why the numbers are what they are. No answer fits, but there is a deeper version of the same question. Not why these numbers, but what are the numbers written in? What is the substance of reality at the most fundamental level? For most of the history of physics, the answer was obvious. Reality is made of matter, atoms, particles, fields, things that occupy space and evolve in time. The constants describe the properties of these things, and the laws describe how they interact. But over the past 30 years, a series of results from completely different areas of physics have converged on a conclusion that nobody planned and nobody expected. The substance of reality may not be matter. It may not be energy. It may not even be space-time. The results suggest that the most fundamental layer is information. Not information in the colloquial sense, not data on a hard drive, not ones and zeros. Information in the physical sense, the irreducible content of a quantum state. The minimum description required to distinguish one configuration of reality from another. This is not philosophy. It is not metaphor. It is the direction in which three independent lines of research are pointing. And each line arrives at the same destination through a different route. The first came from the physics of black holes. The second from the attempt to unify quantum mechanics and gravity. The third from the oldest unsolved question in quantum theory. All three converge on a single statement. Space-time is not the foundation. It is the output. The first line of evidence comes from a calculation that was meant to solve a puzzle about black holes. The question that started was considered naive. In 1972, Jacob Bekenstein, a graduate student at Princeton, asked whether a black hole has entropy. Does a black hole have entropy? If it does, it must have a temperature. If it has a temperature, it must radiate. His advisor, John Wheeler, encouraged him. The physics establishment did not. The most prominent skeptic was Stephen Hawking, who set out to prove Bekenstein wrong. Instead, he proved him right. The proof appeared in 1974. Hawking showed that black holes do radiate. They have a temperature. They have entropy. And the entropy of a black hole is proportional to the area of its event horizon, not the volume, the area. This is strange. Think about a room full of gas. The entropy of the gas depends on the volume of the room because that is where the molecules are. More space means more possible arrangements means more entropy. But for a black hole, the entropy scales with the surface area, not the volume enclosed. The implication was formalized by Gerard Hooft in 1993 and given a name by Leonard Susskind in 1995. The holographic principle. It states that the maximum amount of information that can be contained in any region of space is proportional not to the volume of that region, but to the area of its boundary. The information is on the surface. The three-dimensional interior is a reconstruction. Think about that for a moment. Everything you experience as depth, as distance, as the feeling that objects exist at different points in a three-dimensional space, all of it may be a projection from a two-dimensional boundary. The third dimension is not given. It is computed. That was the first line. The second comes from a deeper crisis. The two most successful theories in physics are quantum mechanics and general relativity. Quantum mechanics describes the behavior of particles, fields, and forces at the smallest scales. General relativity describes the geometry of space-time and the behavior of gravity at the larger scales. Both are verified to extraordinary precision. Neither has ever failed an experimental test. And they are incompatible. They cannot both be true in the same domain. For most of the universe, this does not matter. Gravity is weak, where quantum effects are strong, and quantum effects are negligible, where gravity dominates. The two theories never meet. except in one place: the event horizon of a black hole. In 1974, Hawking showed that black holes radiate, but the radiation is thermal. It carries no information about what fell in. If you drop a book into a black hole and wait for it to evaporate, the radiation that comes out tells you nothing about the book. The information is destroyed. But quantum mechanics forbids the destruction of information. Unitarity, the principle that quantum evolution is reversible, is the foundation of the entire framework. If unitarity is violated, quantum mechanics collapses. For 30 years, this was called the black hole information paradox. Hawking said information is lost. Susskind and Preskill said it is preserved. Hawking conceded in 2004. He paid Preskill an encyclopedia, a symbol of information preserved. But the concession was not a solution. No one showed how the information gets out. Every proposed mechanism generated a new contradiction. The contradictions converged in 2012, when 4 physicists demonstrated that the problem is not a gap in our knowledge. It is a structural impossibility. In 2012, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully published what became known as the AMPS firewall argument. The logic is precise. If information is preserved during black hole evaporation, which quantum mechanics demands, then the quantum entanglement between particles inside and outside the horizon must be broken at the horizon. Breaking entanglement releases energy. The horizon becomes a wall of fire. Anything crossing it is incinerated instantly. But general relativity makes an equally firm prediction. An observer falling into a black hole notices nothing special at the horizon. The equivalence principle, the cornerstone of Einstein's theory, guarantees that free fall through the horizon is indistinguishable from floating in empty space. 2 predictions, 1 point in space. The predictions are mutually exclusive. If the firewall exists, general relativity is wrong at the horizon. If the firewall does not exist, quantum mechanics is wrong about information. There is no middle ground. Both theories cannot survive this point. The physics community spent years trying to find a loophole. The loophole they found was not a fix. In 2013, Maldacena and Susskind did not resolve the paradox. It dissolved the framework in which the paradox was stated. They proposed that quantum entanglement and wormholes are the same thing. The Einstein-Rosen bridge, a geometric connection between 2 distant points in spacetime, is identical to the Einstein-Podolsky-Rosen correlation, the non-local link between entangled particles. ER equals EPR. If this is true, then spacetime geometry is not fundamental. It is built from entanglement. Stitch enough entangled particles together and you get space. Remove the entanglement and space tears apart. The arena on which physics takes place is not given in advance. It is assembled from quantum information. Spacetime is not the stage, it is the show. 3 routes, 3 destinations. The holographic principle says the information content of a region is on its surface, not in its volume. ER equals EPR says spacetime geometry is woven from quantum entanglement. And both of these converge on a single conclusion, stated most clearly by John Archibald Wheeler in 1989. 3 words: it from bit. Wheeler was not a fringe thinker. He was Feynman's doctoral advisor. He coined the terms black hole and wormhole. He was one of the architects of 20th century physics. And at the end of his career, he concluded that the foundation of reality is not material. Every particle, every field, every force derives its existence from the answer to a yes or no question. A binary choice, a bit of information. The universe, Wheeler argued, is not made of stuff. It is made of answers. This sounds like philosophy until you look at where the physics has gone since. Where it went. The ADS/CFT correspondence, formulated by Maldacena in 1997, is the closest thing we have to a working theory of quantum gravity. It states that a gravitational theory in a volume of spacetime is exactly equivalent to a quantum theory, without gravity on the boundary of that volume. The inside and the outside contain the same information. The gravitational, three-dimensional description is a translation of the non-gravitational, two-dimensional description. Neither is more real than the other, but one of them contains space-time and the other does not. If you take the boundary description as fundamental, then space-time, matter, gravity, everything you experience as physical reality is not the input. It is the output of a deeper informational process. If space is a projection and matter is a derivative, and the foundation of reality is information, then one question follows with absolute inevitability. What about time? We treat time as the most obvious feature of existence. Everything happens in time. Causes precede effects. The past is fixed, and the future is open. You remember yesterday, but not tomorrow. This feels so fundamental that questioning it seems absurd. But physics has been questioning it for over a century. And the answers have been consistent. The consistency begins with special relativity. In 1908, Einstein's former professor Hermann Minkowski revealed its full implication. Space and time are not separate. They are a single four-dimensional structure. And within that structure, there is no objective present. No universal now. Two observers moving at different velocities will disagree on which events are simultaneous. Not because of a measurement error, because simultaneity is not a property of the universe, it is a property of the observer. This means the past and the future are as real as the present. They exist. They are out there. The distinction between what has happened and what will happen is not a feature of reality. It is a feature of your perspective. Einstein understood this. When his lifelong friend Michel Besso died in March 1955, Einstein wrote to Besso's family. He said that the distinction between past, present, and future is only a stubbornly persistent illusion. He was not being poetic. He was describing what his own equations say. 1 month later, Einstein himself was dead. The equations survived, and they still say the same thing. Special relativity removed the universal present, but the equations still contain time as a variable. Events still had coordinates in the time dimension, even if observers disagreed on which coordinate was now. Time was relative, but it was there. In 1967, that changed. What changed it was a single equation, written by Wheeler-DeWitt, that describes the quantum state of the entire universe. Not a particle inside the universe, not a field evolving within the universe itself, taken as a single quantum system. He combined the two greatest frameworks in physics. Quantum mechanics provided the structure. General relativity provided the geometry. The result is known as the Wheeler-DeWitt equation. It is the closest thing physics has to a theory of everything applied to cosmology. And it does not contain time. The variable t does not appear. This is not an approximation. It is not a simplification. The equation describes the full quantum state of the universe, and in that description, nothing changes. Nothing evolves. There is no before and there is no after. The equation does not say that time is hard to find. It says that time is not part of the description. Every other equation in physics contains time explicitly. Newton's second law, Maxwell's equations, the Schrödinger equation, the Dirac equation, the Einstein field equations. All of them describe how things change from one moment to the next. The Wheeler-DeWitt equation describes a universe in which there are no moments. It has been nearly 60 years since DeWitt published this result. It has not been overturned. It has not been corrected. It has been avoided. Avoided is not the same as solved. The equation says time is absent, but you experience time. You feel it passing. How do you reconcile a fundamental equation with no time and a conscious experience that is entirely organized around time? The reconciliation came from Carlo Rovelli and Alain Connet in 1994. They called it the thermal time hypothesis. The idea begins with a simple observation. Temperature is not a fundamental property of reality. A single molecule does not have a temperature. Temperature is a statistical property that emerges when you have a large number of particles, and you do not track each one individually. It is a measure of your ignorance about the microstate. You know the average energy, but not the precise configuration. Ravelli and Connors propose that time works the same way. At the fundamental level, the universe is a static quantum state. No change, no flow, no direction. But a macroscopic observer, an entity made of trillions of particles that cannot access the full quantum state, experiences something that feels like change. The observer has incomplete information, and incomplete information generates a perceived flow. What you call time is the thermal consequence of not knowing everything. It is not a feature of the universe, it is a feature of your limitations as an observer within the universe. This is not a minor reinterpretation. If Ravelli is right, time is not fundamental. It does not exist at the deepest level. What exists is a timeless quantum state. Time is what that state looks like from the inside when you do not have access to the whole picture. You are not moving through time. You are a pattern in a static structure that has the property of feeling like it moves. Ravelli explained time as a statistical illusion, but Julian Barber went further. How far he went is in the title of his 1999 book, The End of Time. The title is not metaphorical. Barber's argument starts where DeWitt's equation ends. If the fundamental description of the universe does not contain time, then perhaps we should stop trying to recover it. Perhaps time does not emerge. Perhaps it was never there. Barber proposes that the universe is a collection of static configurations. He calls them nows. Each now is a complete arrangement of every particle and every field, a frozen snapshot. There are unimaginably many of them, but they are not arranged in sequence. There is no timeline connecting one now to the next. There is no next. Each now simply exists. Your experience of motion, of change, of one event following another is not a record of the universe evolving. It is a property of the specific now you are in. That now contains within it a structure that encodes what looks like a memory of a past and what feels like an anticipation of a future. But the past did not happen. The future will not happen. There is only the configuration, and the configuration includes the sensation of time. If this is correct, then causality is an illusion. It does not cause B. A and B are two separate configurations that happen to contain internal structures suggesting a connection. The appearance of cause and effect is like the appearance of motion in a film strip. Each frame is still. The movement is in your perception, not in the frames. Consider what this means for everything we have discussed. Every theory in this video relies on causality. The second law of thermodynamics says entropy increases over time. The Big Rip follows a causal chain of expanding forces. Vacuum decay is a process that unfolds in time. If time and causality are not real, then the instrument we have been using to evaluate every threat is itself in question. Every prediction in this video assumes that causes produce effects. That assumption may not hold. Space is not fundamental. Time may not exist. Causality is in question. But we are still here. We are still observing. Whatever the ultimate nature of reality turns out to be, one thing appears to be solid. We look at the universe and we see things. We collect data. We measure. Observation is the bedrock of science. If everything else is uncertain, at least the act of looking is real. Quantum mechanics has been saying something about this for 100 years. And what it says is the opposite of comforting. The measurement problem is the oldest unsolved question in physics. It was there at the birth of quantum theory, and it has not moved since. The equations of quantum mechanics describe a particle not as a thing with a definite position or momentum, but as a wave function, a mathematical object that encodes every possible state the particle could be in, all at once. The particle is not in one place. It is in a superposition of all possible places. This is not a statement about our ignorance. It is a statement about reality. The particle does not have a definite state that we simply do not know. It does not have a definite state at all, until you measure it. The moment you perform a measurement, the wave function collapses. The superposition disappears. The particle is found in one specific location. The other possibilities vanish. Quantum mechanics describes this transition perfectly. It predicts the probabilities of every possible outcome with staggering accuracy. But it does not explain why the collapse happens. It does not explain what a measurement is. It does not explain what makes an observer different from any other physical system. Niels Bohr, who established the Copenhagen interpretation, essentially told physicists not to ask. The theory works. Use it. Do not ask what happens between measurements. For 100 years, most physicists have followed that instruction. The few who did not were told they were doing philosophy, not physics. The question did not go away. It got worse. In 1978, John Archibald Wheeler proposed an experiment designed to push the measurement problem to its breaking point. He called it the delayed choice experiment. The delayed choice begins like every quantum experiment, with a double slit. A photon is sent toward a barrier with two slits. If you do not observe which slit the photon passes through, it behaves as a wave. It goes through both slits simultaneously and produces an interference pattern on the detector. If you do observe which slit it passes through, it behaves as a particle. It goes through one slit, and the interference pattern disappears. This much was known since the 1920s. Wheeler's addition was a single change. He proposed making the decision to observe or not observe after the photon has already passed through the slits. The photon is in flight. It has already done whatever it is going to do. Then you decide whether to look. The experiment remained a thought experiment for 29 years, until Vincent Jacques and colleagues performed it in 2007. The result confirmed Wheeler's prediction. When the decision to observe was made after the photon had passed through the barrier, the photon's behavior changed retroactively. If the detector was set to observe, the photon had gone through one slit. If the detector was set to not observe, the photon had gone through both. The decision you make now determines what happened in the past. Not what you know about the past, what happened. The photon did not have a history until you chose to look. Your observation did not reveal a pre-existing fact. It created one, and it created it backward in time. The delayed choice experiment showed that the act of observation determines what happened. But there is a stranger result. The stranger result came in 1999, from the quantum eraser experiment performed by Yoon-Ho Kim and colleagues. The setup begins the same way. Photons are sent through a double slit, but this time, each photon is entangled with a partner. The partner carries information about which slit the original photon went through. As long as that information exists anywhere in the system, the interference pattern disappears. The photon behaves as a particle. Then the experimenters erased the information. They destroyed the record of which slit the partner photon indicated. And the interference pattern came back. The photon retroactively behaved as a wave, not because the photon changed. The photon had already hit the detector. What changed was the information available in the system. When the information existed, the photon was a particle. When the information was erased, the photon was a wave. The same photon. The same detector. The same moment of impact. Two different realities, determined not by what happened, but by what is known. This is not an interpretation. It is a measurement. The experiment has been repeated in multiple laboratories with consistent results. And it says something very specific about the relationship between information and reality. Reality does not exist independently of what is known about it. The state of a system is not fixed by the events that occurred. It is fixed by the information that is preserved. Erase the information and the reality changes. Not your knowledge of the reality itself. Observation determines the state. Observation creates the past. Observation selects reality based on information. There is one more result. The prediction came in 1977 from Baidyanath Misra and George Sudarshan. Continuous observation should freeze a quantum system in place. A radioactive atom, left alone, will decay. Its wave function evolves, and at some point, the atom transitions to a lower energy state. But if you measure the atom repeatedly, fast enough, the wave function never has time to evolve. Each measurement resets the clock. The atom stays in its initial state indefinitely. Misra and Sudarshan called this the quantum Zeno effect, after the ancient philosopher who argued that motion is impossible because at any given instant, an arrow is at rest. 13 years later, Wayne Itano and colleagues at NIST confirmed it experimentally. They trapped beryllium ions and applied a series of rapid measurements. The ions that were observed frequently remained in their initial state. The ions that were left alone transitioned normally. The experiment has been replicated and extended in the decades since. The result is unambiguous. If you watch a quantum system, it stops changing. If you look away, it resumes. Observation is not a passive act. It is not a window through which you view an independent reality. Observation is an intervention. It determines what exists. It determines when it exists. It can create the past and freeze the present. And this raises a question that physics has been avoiding since 1927. If observation has this much power over reality, then what exactly is an observer? What property does a system need to have in order to count as a measurement? What is it about you that makes the wave function collapse? Because if the answer involves consciousness, then physics has a problem it cannot solve with physics. The problem has a name. David Chalmers named it in 1995. The hard problem of consciousness. The easy problems of consciousness are not easy in the ordinary sense. They are the problems that neuroscience is equipped to solve in principle. How does the brain process visual information? How does it form memories? How does it coordinate motor responses? These are engineering problems. They are enormously complex, but they are the kind of problems that yield to reductionist analysis. You study the components and you eventually understand the system. The hard problem is different. It asks a question that no amount of neuroscience can answer by studying components. Why is there subjective experience at all? You can describe every neuron that fires when a person sees the color red. You can map the exact electrical and chemical cascade from the retina to the visual cortex. You can build a complete model of the process, and you still have not explained why there is something it is like to see red. Why the experience exists. Why it is not just information processing in the dark. A computer can detect a wavelength of 700 nanometers. It can classify it. It can respond to it. But there is nothing it is like to be that computer. There is no inner experience. The question is, what makes you different? What generates the qualitative, subjective, first-person experience that you have and that the computer does not? In 30 years since Chalmers formulated the problem, no theory in neuroscience, no theory in physics has provided a mechanism that bridges the gap between physical process and subjective experience. Correlation has been found in abundance. Mechanism has not. And the reason the physics community avoids this topic is not that it is unscientific. It is that every serious path toward an answer leads outside the boundaries of physics as currently defined. The first physicist to take that path seriously was Roger Penrose, who published The Emperor's New Mind in 1989, in which he argued that consciousness cannot be the product of computation alone. His reasoning was rooted in Gödel's incompleteness theorem. If the mind were a computer, it would be subject to the same limitations that Gödel proved apply to all formal systems. There would be truths it could not reach, but mathematicians do reach those truths. Therefore, Penrose concluded, the mind is doing something that is not computation. The mechanism they proposed in 1996 is called orchestrated objective reduction, or ORC-OR. The theory locates consciousness in quantum processes occurring inside microtubules, protein structures within neurons. According to ORC-OR, the collapse of the wave function in these microtubules is not random. It is orchestrated by the geometry of spacetime itself. Consciousness in this model is not produced by the brain. It is a quantum gravitational process that the brain is tuned to access. The reception was hostile. Most neuroscientists dismissed the idea as implausible. Most physicists dismissed it as untestable. Hameroff's microtubules were called too warm, too wet, and too noisy for quantum effects to survive. For 2 decades, OR was treated as an embarrassment. But in the years since, experimental evidence for quantum coherence in biological systems has accumulated. Photosynthesis appears to use quantum effects to optimize energy transfer. Bird navigation may rely on quantum entanglement in cryptochrome proteins. The categorical claim that quantum effects cannot occur in warm, wet biological systems is no longer tenable. OR has not been confirmed, but it has not been replaced. And the problem it was built to solve, the hard problem, remains exactly where Chalmers left it. There is another approach that does not rely on quantum gravity or microtubules. The alternative appeared in 2004 when the neuroscientist Giulio Tononi proposed integrated information theory, or IIT. The core claim is simple and radical. Consciousness is not a biological phenomenon, it is a mathematical one. Tononi defined a quantity he called phi. Phi measures the amount of integrated information in a system. Integrated means that the information cannot be reduced to the information contained in the system's parts. It is information that exists only because the parts are connected in a specific way. The higher the phi, the more conscious the system. A human brain has a high phi. A collection of disconnected neurons has a low phi. A thermostat has a tiny but non-zero phi. The implications are immediate. If consciousness is phi, then consciousness is not tied to biology. It is tied to the structure of information integration. Any system with sufficient phi is conscious. Carbon-based, silicon-based, something else entirely. The substrate does not matter. The math does. The question stopped being hypothetical in 2019 when Alison Mootri at the University of California, San Diego grew brain organoids in a laboratory. Clusters of human neurons, self-organized in a dish, with no body and no sensory input. The organoids generated electrical activity patterns that matched the patterns seen in premature human infants. They exhibited measurable phi. The question of whether a clump of cells in a dish is conscious is not a thought experiment. It is an experimental result waiting for a framework to interpret it. And the framework IIT provides says yes. If the PHI is there, the experience is there, regardless of whether the system has eyes or a body or a name. If consciousness is a mathematical quantity that depends on the structure of information, and if the foundation of reality is itself information, then a conclusion follows that most physicists will not say out loud. Consciousness may not be a product of the universe, it may be a property of the universe. This position has a name: panpsychism. It proposes that consciousness is not something that emerges at a certain level of complexity, the way wetness emerges from water molecules. It proposes that consciousness is fundamental, present at every level, not in the sense that an electron thinks or a rock has feelings, but in the sense that the capacity for experience is woven into the fabric of reality the same way charge or spin is woven into the fabric of particles. This is not a New Age fantasy. It is a position held by serious philosophers and increasingly discussed by physicists. The list of defenders is not short. Chalmers considers panpsychism the most promising path. Koch argues IIT leads there naturally, and Goff has published rigorous philosophical defenses. The logic is straightforward. Physics describes the behavior of matter. It tells you what matter does. It does not tell you what matter is. It gives you equations, not essences. Panpsychism fills the gap. It proposes that the intrinsic nature of matter, the thing that physics describes only from the outside, is experiential. Not human experience, not thought, something far more primitive, a basic capacity for being. And here is why this theory belongs in a video about theories scientists are afraid to talk about. The logic is defensible. The philosophy is rigorous. The compatibility with IIT is real, and almost no physicist will attach their name to it in a published paper. Because the word consciousness in a physics department ends conversations. It does not start them. Consciousness ends conversations in physics departments, but the model that started this conversation is still on the table, and it has one more problem. We followed the cracks downward, through the fate of the universe, through the instability of the vacuum, through the fine-tuning of the constants, through the dissolution of space-time, through the disappearance of time, through the power of observation, through the mystery of consciousness. At every level, we found that what seemed solid was contingent, what seemed permanent was fragile, what seemed fundamental was derived. Now we return to the model itself, because the model has one more problem, and it is not a crack from outside. It is a contradiction built into the foundations. The contradiction was exposed in 2002, when Lisa Dyson, Matthew Kleben, and Leonard Susskind treated the standard cosmological model with full statistical rigor. They asked a simple question. If the universe lasts forever, and if quantum fluctuations continue to occur in the vacuum of empty space, what kinds of observers will the universe eventually produce? The answer was disturbing. Over an infinite timeline, random thermal fluctuations will spontaneously assemble every possible configuration of matter, including a brain. A fully formed brain, complete with neurons, synaptic connections, and a complete set of false memories. A brain that believes it has a past, believes it has a body, believes it is reading a sentence right now. This is a Boltzmann brain. It is named after Ludwig Boltzmann, who first encountered the statistical paradox in 1896. And the problem is not that Boltzmann brains are possible. The problem is that they are overwhelmingly more probable than you. The arithmetic is relentless. A real observer like you requires a very specific history. A Big Bang, billions of years of cooling, the formation of galaxies and stars, the nucleosynthesis of heavy elements, the assembly of a planet in the habitable zone, the emergence of life, billions of years of evolution, the development of a nervous system complex enough to support consciousness. Each step is improbable. The total probability of producing you through the standard cosmological process is extraordinarily small. A Boltzmann brain requires none of that. It requires a single thermal fluctuation of sufficient size to assemble a brain-sized configuration of matter with the right structure. That fluctuation is also extraordinarily improbable, but it is less improbable than the chain of events that produced you. And in an infinite universe with infinite time, the less improbable event happens infinitely more often. The ratio is not close. For every real observer produced by stars and planets and evolution, the model predicts an effectively infinite number of Boltzmann brains. Momentary assemblies that flash into existence with a complete set of memories observe one instant of apparent reality and dissolve back into thermal noise. If you take the model seriously, and if you accept that you are a typical observer, then you are almost certainly one of them. Your memories are fabrications. Your past did not happen. The universe you think you see is a momentary hallucination that will be gone before the next thought forms. This sounds absurd, but the problem is not the absurdity. The problem is that this is a direct mathematical consequence of the standard model of cosmology. The same model that predicted the cosmic microwave background. The same model that earned the Nobel Prize. The model does not produce this result as a fringe case. It produces it as the dominant prediction. There is a response that might seem obvious. Just fix the model. Adjust the parameters. Add a term. Physicists fix models all the time. But this problem is different. It is not a bug in the calculation. It is a consequence of the logic. The trap was described precisely by Sean Carroll, Kimberly Boddy, and Jason Pollock in 2016. They called it cognitive instability. The argument runs as follows. If the model predicts that most observers are Boltzmann brains, then most observations are produced by Boltzmann brains. A Boltzmann brain's observations are random. they do not reflect the actual state of the universe. They reflect a momentary fluctuation that happens to look like a universe. This means that the data we use to build the model, the cosmic microwave background measurements, the supernova distances, the galaxy surveys, are, according to the model itself, almost certainly not real data. They are hallucinated data. The model predicts that the evidence for the model is fake. Think about what this means. You build a model. The model works. It passes every test. Then you follow the model to its logical conclusion, and the conclusion tells you that the tests were not real. The model has not failed an external check. It has consumed itself. This is not a paradox that can be resolved by better data, because the model says the data cannot be trusted. It is not a paradox that can be resolved by better math, because the math is the source of the problem. The instrument has turned on itself. It is a machine that produces a prediction that invalidates the machine. Physicists have tried to escape this. The escape attempts are well documented. Andrea de Simone and colleagues catalogued one class of them in a 2010 paper titled Boltzmann Brains and the Scale Factor, Cutoff Measure of the Multiverse. The strategies fall into three categories. The first is to make the universe finite. If the universe has a finite lifetime, the number of Boltzmann brains it can produce is also finite. In some versions, the real observers outnumber the fluctuations. The problem is that we do not know whether the universe is finite. Nothing in the current model requires it to be. You would have to add the assumption by hand, and the assumption has no independent justification. The second strategy is to change the measure. In an infinite universe, you need a rule for counting observers. Different rules give different answers. Some rules suppress Boltzmann brains, but there is no consensus on which rule is correct. Every proposed measure introduces its own paradoxes. You solve the Boltzmann brain problem and create a new one. The third strategy is to declare that the model is broken and search for a replacement. This is the honest option. It is also the most frightening. Because Lambda-CDM is not a marginal theory, it is the framework on which the past 25 years of cosmology are built. Every result in this video, from the expansion of the universe to the mass of the Higgs boson, was interpreted within this framework. If the framework is broken, we do not simply lose a model. We lose the context in which every other result makes sense, and no replacement exists. There are proposals, modified gravity, dynamical dark energy, holographic cosmology. None of them are complete. None of them have passed the test that Lambda-CDM passed before it began to fail. The framework we use to interpret reality has undermined itself, and nothing has taken its place. Perhaps the problem is not the model. Perhaps it is deeper than any model. The proof that sets the ceiling was written in 1931 by a 25-year-old Austrian logician named Kurt Gödel, and it shattered the foundations of mathematics. He demonstrated that in any formal system powerful enough to describe arithmetic, there exist true statements that the system cannot prove, not statements that are unknown, statements that are true and that the system is structurally incapable of reaching. The system is incomplete, not because it is poorly designed, because incompleteness is a necessary property of any sufficiently complex formal system. Gödel set the limit for logic. 5 years later, Alan Turing set the same limit for computation. He showed that there exist well-defined problems that no algorithm can solve, not problems that are too hard, problems that are unsolvable in principle. No amount of time, no amount of computational power, no cleverness of design can reach the answer. The system has a ceiling, and the ceiling is not a limit of technology. It is a limit of logic. Now consider what this means for physics. Physics is a formal system. It uses mathematics to describe reality. It makes predictions and tests them against observations. If Gödel is right, and he is, because the proof has been verified and reaffirmed for nearly a century, then any physical theory powerful enough to describe the universe will contain truths about the universe that the theory cannot derive. There will always be questions that physics can pose but cannot answer. Not because we are not smart enough, because the structure of logic does not permit it. The universe may contain facts about itself that no internal observer can ever discover. Not hidden facts, not encrypted facts, facts that are formally unreachable from inside the system. Mathematics set the ceiling. The universe is building the walls. The walls were measured in 2007 when Lawrence Krauss and Robert Scherer described what observational cosmology will look like in the distant future. The answer is bleak. The universe is expanding. The expansion is accelerating. Galaxies beyond our local group are receding from us faster with every passing year. At some point, they will cross the cosmological horizon. The light they emit will never reach us. They will not dim. They will not fade. They will simply become unreachable, gone in a way that is more final than destruction, because destruction leaves evidence. Once a galaxy crosses the horizon, it is as though it never existed. Krauss and Scherer calculated the timeline. In roughly 100 billion years, every galaxy outside our local group will have vanished beyond the horizon. The cosmic microwave background, the afterglow of the Big Bang, will have redshifted to wavelengths so long that no instrument could ever detect them. The evidence for the Big Bang itself will be gone. A civilization arising at that time would look out at the universe and see a single galaxy surrounded by empty, static, eternal darkness. They would conclude, reasonably and incorrectly, that the universe has always been this way. They would have no data to suggest otherwise. The universe would have erased its own history. But the erasure is not only in the future. Cosmic inflation, the exponential expansion in the first fraction of a second, has already erased the initial conditions of the universe. Whatever existed before inflation, whatever set the parameters, whatever determined the topology, that information was stretched beyond any possible recovery. We cannot see what came before. Future civilizations will not see what is here now. The past has been deleted. The future will be deleted. The closing has a timeline. Abraham Loeb calculated it in 2002, and few people discuss what he found. He asked a simple question. For how long will the cosmological data that we currently use to understand the universe remain available to any observer? The answer is finite. The cosmic microwave background is detectable now. In 100 billion years, it will not be. The baryon acoustic oscillation signal, the pattern that DESI measures, depends on seeing galaxies at a range of distances. When those galaxies cross the horizon, the signal goes with them. The Type 1a supernovae that revealed the acceleration of the universe can only be calibrated against objects in galaxies we can still see. When those galaxies are gone, the method fails. Loeb's conclusion is precise. There is a window of time during which an observer inside this universe can gather enough data to reconstruct cosmology. We are inside that window right now. It will not remain open. The observations that revealed dark energy, that measured the expansion rate, that detected the CMB, that built the Lambda-CDM model, all of them are possible only because we happen to exist at the right moment in cosmic history. A civilization that arises too late will not know that the universe is expanding, will not know that a Big Bang occurred, will not know that dark energy exists. They will ask the same questions we ask, and the universe will give them no answers. Not because the answers are hidden, because the evidence has been carried beyond the horizon by the expansion of space itself. We are not the smartest observers in the history of the cosmos. We are the luckiest. We exist in the only epoch when the universe is willing to show its hand. And that epoch is ending. This is what the equations say. We started with a model that worked for 25 years and watched it crack under the weight of new data. Behind the first crack, we found that the fate of the universe is not settled. It may burn out slowly. It may be torn apart. It may collapse back on itself. Behind the second crack, we found that the laws of physics themselves are not permanent. The vacuum that sustains them is balanced on a ledge that quantum mechanics says will eventually give way. Behind the third, we found that the constants governing reality are set with a precision that has no explanation. Not an unknown explanation, no explanation. Behind the fourth, we found that space and time, the stage on which all of this plays out, are not fundamental. They are projections of something deeper. Information. Behind the fifth, we found that the act of observing reality does not record it. It creates it. Behind the sixth, we found that the one thing doing the observing, consciousness, is the one thing physics cannot account for. And behind the last crack, we found that the model itself, the instrument we use to see all of this, predicts that the observer is most likely not real. The equations did not fail. They did not mislead. They described reality with extraordinary precision. And the reality they described is one in which nothing is permanent. Not matter, not space, not time, not the laws, not the model, not the observer, and not the window through which we saw it all. That window is closing. What physicists are afraid to talk about is not any single one of these results. Each one, taken alone, can be managed, contained, published with caveats, discussed at conferences with careful language. What they are afraid of is the direction. Every deeper layer of reality, examined honestly, is less stable than the layer above it. Each foundation rests on something less certain, and at the bottom there is nothing at all. And the tools we built to look down are themselves part of the structure that is falling. We looked into the equations, and the equations looked back. What they showed us is not a universe that makes sense. It is a universe that makes predictions, and the predictions are correct, and they are terrifying, and no one knows what to do about them.